Good evening, everyone. Thank you for taking time to listen to my presentation. I'm glad to be presenting my paper titled System Dynamics Across 3 Scales in the Brahmaputra River Basin, Exploring a Himalayan Social-Hydrological System. With me is Dr. Varma, who has co-authored the paper and has kindly offered to take time off to co-present our work together today. To start, I would like to discuss the possible relevance of our work. What we are essentially offering with our research is the use of system dynamics to identify the multi-cross-scale interactions in a political and ecologically fragile river basin system of the Global South. Our research can offer an operational framework for applying a social hydrological approach for exploring and solving issues of river basin governance. We hope our conference sharing will be insightful for our audiences today. Moving along, here is a brief overview of our presentation. We will bring you through the stages of our methodology and finally end off with key insights of the research work. For the conceptualization stage, I shall let Dr. Varma explain more about how we have thought about the individual subsystems.
Thank you, Ryan. So Ryan and I are essentially talking about the huge river system which starts from the Tibetan plateau as Yalung Zangpo, flows through the northeast of India as the Brahmaputra, and goes towards Bangladesh as Jamuna before falling into the Bay of Bengal Sea. Case study-wise, we are actually talking about the state of Assam in India, in northeast of India. And you can see the remote sensing imagery of the situation of the river since the late 70s to early 2000, which is basically the river has become multiple channeled. And you can also see the trend of the high flood level, which is kind of plateauing, but that does not give any respite to the breaches in the embankment in our case study area. The stars in the diagram actually represent the events of embankment breaches. And Ryan will be talking more about these patterns. Next slide. So here is a brief description through imagery about the problem situation. So the problem in the villages of a particular district within the Assam state has shifted to one of landlessness from flood. So the villagers who are paddy farmers are losing land due to riverbank erosion, then due to coarse sediment deposition, and also due to the policy of embankment maintenance and reconstruction, because as the river erodes the land as well as the embankment, the new embankment has to be rebuilt few meters away from the villages. So the new land for embankment construction is actually acquired from the villagers. Next slide, please. So these are some photographs from fieldwork done from 2011 to 2015 and 16, which gives you a flavor of the changes in the entire system in different seasons. In the monsoon, it may look just like a whole seascape, whereas in the dry season, it may look like a desert due to coarse sediment deposition. The state government in India has reacted by building a new kind of embankment known as the geotextile embankment, which not only protects the area from flood, but also from bank erosion. Next slide, please. So what we did from our field work is that we tried to use systems thinking, and we identified that there were around 4 narratives of the same flood and erosion problem. Next slide, please. So here are the 4 narratives from the Water Resource Department. They feel that they are doing it right with their embankments. The riparian community, known as the Mishing community, feel that they are neglected because the problem has moved towards landlessness from flood. Other departments like the revenue and disaster management feel that the villagers, the tribe, the community is the problem, because they do not shift away from this risk-prone area, and rather they build their settlements over the embankment. The academia feel that it is not the issue of few villages or a province, but it's a whole problem of the river basin, where after a huge earthquake of 1950, there have been changes in the river width and depth, and as a result, there have been cultural issues within the community. So these narratives appear as though they have their own spatial and temporal scales. Next slide, please. So we did a group modeling exercise way back in 2014-15, where we could learn some of the opportunities and challenges for shared understanding and vision for policy in such fragile river basin. However, it is only now that Ryan and our co-authors together, we are trying to understand and organize this knowledge into 3 distinct subsystems in 3 scales of the river basin. I pass on the time to Ryan for further explanation.
Next, with the understanding of these narratives, we look towards understanding how they interact as a whole. We get much of our inspiration from the Bernanke framework of social-ecological systems, and it provides a conceptual lens to explore cross-scale interactions within the elaborated subsystems, namely socio-economic situation of the villages, flood control policies, and the geomorphology, which exists on varying spatial temporal scales, as explained before and as illustrated on this diagram. To put it simply, as opposed to hierarchy, which is mainly top-down, Bernanke proposes a system structure that can be influenced from top to bottom and bottom to top. The mesocycle of the system will often be influenced both by the slow-moving processes of a macrocycle and also the fast-moving processes of a microcycle. Hence, by conceptualizing the complexity within and across different scales, we explore the dynamics in the behavior of the system, as certain processes can change at any of the system scales. This can potentially provide insights into our problem context. As such, we have developed a causal loop diagram that qualitatively expresses the narrative of our problem context. The macro subsystem, which represents the geomorphology, is placed on the left box. The micro subsystem, which represents the socio-economic village dynamics, are on the right. And finally, the meso subsystem, which represents the flood control policy, is mainly the variables and loops that interact between the previously mentioned subsystems. Next, we proceed with the stock and flow diagram, which is based on the previously discussed CLD for simulation. We found a need to conceptualize and develop the SMD in a rather unique way, as we ran into several difficulties, mainly to the cross-scale nature of our system. Firstly, there was difficulty linking the variables in each subsystem. As such, we model our SFD around tracking the sediment flow, as it appears to be the only physical quantity that is shared between each subsystem. However, it comes with the problem of unit scaling. For instance, it is hard to quantitatively present the flow from the sediment bed load to the deposition of the riverbank, since essentially one variable measures the whole river basin and the other variable measures a much smaller area of study. So to solve this, we make a rather daring but reasonable assumption that these variables meet on a physically comparable scale, like for example a cross-section of a river, but yet is still representative of the subsystem on its respective scale. We use arbitrary units and scaling parameters to keep this unit consistency in check. Finally, it was also rather challenging to model the numerical values, since we do not have much data to work with in the first place due to the political sensitivity of this case study. Hence, much of our focus lies in studying the system structures and behavioral trends. So here's the complete diagram. More information about the individual variables can be found in our supporting materials. Next, we have our validation process to ensure the reliability and the robustness of our model. We explored various means of model validation for different areas of testing. Overall, we place a greater emphasis on structural validation, as the purpose of our model is less of a predictive one, but more of a causal descriptive model that is used to study its internal operations and interactions. For a start, we work with a reference mode of important variables from subsystems of different scales. However, we will not focus on the statistical alignment of the simulated data to the historical data, but rather to use it as a theoretical alignment to understand the possible underlying system structure that causes these behavioral trends. We also conducted extreme conditions tests, both direct and indirect, to further validate the reliability of the model in representing interactions within the subsystem and across subsystems. This is done by setting the extremities of the following parameters and observing how it influences key variables on different subsystems. Finally, we did a time-step test to further examine the technical reliability of the model. This is especially necessary when our variables do simulate different kinds of data flows, namely continuous, discrete, and logical, and they are known to act differently with changes to time steps. So moving on to the analysis, I will present some findings from the simulation results and scenario testing. Firstly, we were interested to study the cross-scale linkages between subsystems, more specifically, the impact of village-level dynamics on embankment effectiveness. We wanted to investigate the extent to which protests have increased embankment breaches. We tested a scenario in which the effects of protests are hypothetically mitigated. The results are illustrated here, where the simulated embankment breaches are greatly reduced. Unintuitively, this implies that the exponential rise after year 2000 seems to be caused by the village disruptions during this period. Contextually, the more that we investigate, this also seems to make a fair amount of sense, as based on the simulation of other factors that contribute to embankment failures, namely the high flood levels, they seem to be rather stabilizing, and this intensified trend of breaching has to arrive from somewhere. Subsequently, we tried to trace the cause of these rapid changes in descent that started emerging after the turning point of year 2000. From analysis, it was found out that the irregularity in compensation seems to be the main source of escalation of protests, which started to be more prominent post-1998. This affected the villagers' livelihoods, which led to the discontent and more recent years of embankment disruptions as a result. As such, the following scenario testing has helped us identify unintuitive cross-scale interactions that played a crucial role in shaping the emerging problems. Another aspect studied in our analysis was the opportunities of emerging land. Based on our simulation results, it was found that even though effective usable land for farming has been decreasing, the area of sand islands is potentially rising. This can be interpreted as not only an increase in the number of sandbars and islands, but starting the process of reconnection of such spaces with floodplains, as already observed in many of the areas in the upper river as a result of fieldwork and examination of satellite images. This simulation of sand islands doesn't serve to forecast exact numbers, but rather to highlight a real need for innovations in land use. Furthermore, previous workshop discussions also showed that the community was willing to innovate the practice of land use since they already have cultural legacies of dynamic land use in sand islands. However, even as of 2017, there has been a lack of land surveys to capitalize on these potentials. Next, we will share our policy testing and the insight we gained from simulating possible alternatives. The goal of these policy alternatives is to examine the effectiveness in mitigating the problems with flooding and landlessness, and hence the changes to embankment breaches and effective usable land is observed. We tested 3 policies that are quite probable, either as practices that are used in neighboring communities or as solutions commonly explored given a similar problem context, and each of the individual policies deal with a variable in their respective subsystem as listed on the table. To summarize, we notice that individual policies tend to only alleviate either problem of flood control or landlessness in limited effectiveness. However, when tested with a combination of policies from 1 to 3, it seems that only then the results are fairly significant. We thought that this observation in policy testing make a simple but yet an important point about the necessity of combining interventions at different scales. Such multi-scale disaster management is imperative to build up capacity for long-term disaster management. Finally, here are the takeaways from our research. Firstly, We found the use of system dynamics to be rather useful in exploring the cross-scale dynamics of the Brahmaputra River Basin context and can be replicated for similar fragile river basin systems. The findings from the model has greatly emphasized the role of feedback between issues of governance occurring on the local scale and disaster policy implementations. Our findings also imply a need for flexibility in disaster management institutions to recognize social needs and facilitate adaptation to novel hazards. Flood disaster policy in fragile river systems like the Himalayan need to look at interventions in multiple scales and integrate the dynamics of land use, land tenure, water discharge, and sediment flow. Finally, we believe that system thinking and system dynamics can serve as a pedagogic tool in capacity building programs, which can help in integration of actors' voice, as well as lead to change in mindset and protocols through interactions, dialogues, and simulations. Thank you very much for listening. We've come to the end of our presentation. Thank you.